Welcome to another unit of the ISM course in Statistics 2. This time with a unit on the coefficient of determination and the f-test. Well, consider we already performed a linear regression. We got our coefficients, we tested for each coefficient by itself whether it's having a significant impact or not. But we still want to know something about the overall quality of the model we just built, we just estimated. That's where the coefficient of determination and the f-test come into play. Well, maybe you recall from earlier courses the coefficient of determination, which is basically the share of the variance of the dependent variable, which can be explained by the independent variables, so to speak, by the model itself. And well, the f-test just tells us whether what is explained here is a significant share of the overall, situation, of the overall variance. And well, how do we proceed with this? Well, first we can recall what we actually do when we do a regression. Well, we have this set of data points. We try to fit a line here, which is as close as possible to these data points as possible. So for each of the points, we note the coordinates of the point, in particular the coordinate on the y-axis, so on the axis for the dependent variable, and the corresponding y-coordinate of the regression line, which we want to estimate, which is here written as y hat. Then we're not considering purely the distance from the point on the y-axis to the line, but we consider the squared distance. More on why we use the squared distance can be found in the corresponding course for the Statistics 1. And well, if we have done this, we can use this information to argue that, well, whatever is left here, that's more or less the variance part, which we cannot explain. But, well, we go one step back even more. Imagine we do not have any information at all. Imagine we don't have any access. Well, then the best guess for estimating y would actually be the average of y. So this is the unexplained variance, and here the average of y would be the best guess if I do not have any information. So the distance from our data point, so the yi, to the average, and here the squared ones, would be similar to the total variance of each of the whole data, or whole data set. So the overall variance can be split into the part which is unexplained, that's what still remains, even if we have the regression line, and the part which is explained by moving away from the average via the line. That's this part here. So the small square, that's what still remains as unexplained variance. The large square, that's the variance we can explain by having our regression model, having our regression line. And well, both of them together make up the total variance. And if we just recall this, then the r squared is nothing else than simply the explained variance divided by the total variance. And this looks as follows. Okay, so far so good. So that's just the definition of what the r squared, what the coefficient of determination is. And this tells us the share of the explained variance. And this can be used in an f-test to find out if the overall model has explanatory power, significant explanatory power. However, what the model actually tests is whether that's the H0 hypothesis, no of our coefficients is significantly different from 0, or H1, at least one of the coefficients is significantly different from 0. So here, this was again the formula for the coefficient of determination, different ways of calculating this. And we know this is between 0 and 1, but still we cannot run a test for this. So even if we can simplify this, the first thing we need for any test, we need to determine our H0 and H1 hypothesis. And those are actually not built around the R squared in any way they were defined in the slide before, but they are built around the different coefficients. And we can say H0 means that all the coefficients are 0 at the same time, or in other words, this means there is no relationship between any of our independent variables and the one dependent variable. Or again, put into different words, the model has no explanatory power. The exact logical opposite to this, the H1 hypothesis, then reads as at least one of the xi has a significant impact on y. Or in other words, one of the coefficients is significantly different from 0, at least one of them, and or the model has significant explanatory power. And that's what we're actually going to test, whether at least one of the coefficients is significantly different from 0. But the test statistic we use for this looks a little bit different. So here our test statistic boils down to an F statistic. What we're doing here, what we're using here, is more or less, let's call this transformed version of the explained variance. That's the R squared, and divided by k, the number of independent variables. So that's the part which is explained via the regression line. This is divided by 1 minus R squared, divided by the number of observations, minus k minus 1. So that's more or less, again, the transformed, unexplained part of the variance. So we're basically dividing explained variance by unexplained variance and take a look which of them is significantly larger. We could go into more detail here, but it would make a bit more sense if we actually narrow this down from the point of view of a variance analysis, because this is basically where this comes from. So this would open, however, a very big box in this context. So here, just recall the upper fraction, that's more or less the transformed explained variance. The lower fraction, that's the unexplained variance. And well, we have a test statistic, then we need the corresponding reference statistic. Here, as I said, we use an F distribution. So in an F distribution, we always have 2 degrees of freedom. And that's also the 2 we already see in a test statistic. The first value, that's k, the number of independent variables. And the second one, that's n minus k minus 1. So the number of observations minus the number of independent variables minus 1. And then we have 1 minus alpha, alpha being the marginal error, the acceptable marginal error. Okay, and this we can look up in a corresponding table. As now we have 3 values, there's usually one table for each 1 minus alpha percentage. So here we have the first value, the k, which we have to look up in the corresponding column. And we have the second value, the n minus k minus 1, which we have to look up in the corresponding row. So here in this situation, for example, where k is 1, so we were to have one independent variable, and we have 5 observations. So n is 5 minus 1 minus 1 gives us a second degree of freedom of 3. We would use as reference statistic 10.128. Okay, so far so good. So this tells us how we can get the reference statistic. Then we have the test and the reference statistic. And well, the test itself is relatively straightforward because it works like all the other tests. we compare test and reference statistic. And if the test statistic is smaller than the reference statistic, we retain H0. And if the test statistic is larger, we actually reject H0. And well, that's all there is to conducting an F-test. So let's have a look how this works if we actually consider a practical example for this. Here in our example, we have this table. In this context, I already provided, aside from the variables x and y, and the values, their average, and as well y squared and y hat squared, and their averages. So basically we can just plug this into our formula for r squared, giving us here an r squared of 0.1346. And if we have this r squared, we can use this to actually then calculate our test statistic and find the reference statistic. So I just copy this, the r squared. We have 5 observations. We have 1 x variable, so k is 1. And well, let's start here with an alpha of 5%. Then the test statistic results from this formula as seen before. So we take r squared divided by 1, because we only have 1 x, 1 independent variable, divided by 1 minus r squared, that's a 1 minus 0.1346, divided by 5, number of observations, minus 1, number of independent variables, minus 1 again. And well, if we have this here, enter this into calculator, we get a test statistic of 0.4666. That's the first part. The second part then is the reference statistic. Here we need f, k, n minus k minus 1, 1 minus alpha. So k is 1. Then we have 5 minus 1 minus 1, that's 3. And 1 minus 5% is 0.95. So we have to look up the value f130.95. So we take the table for 0.95. Take a look in, this is column 1 because the first value is 1, and row 3 because the second value is 3. And here we find the value 10.128. So that's our reference statistic. This value we compare with the test statistic. And we see, well, test statistic clearly is smaller than the reference statistic. So we have to retain H0, and we can conclude that our model does not have any significant explanatory power. And well, that's all there is in this context, in this unit. So I hope you liked it. Hope you understand a little bit what this was about. And if you want to see more on this topic or see some additional exercises, feel free to visit the rest of the course or have a look in the corresponding playlist. I say goodbye and see you next time.